Hello everyone. Thank you for coming to attend day 5 of Gem Hunt 2021. Over the week, we've learned from incredible women in math, and I'm sad to see that the program is coming to a close. Nonetheless, I hope you have all enjoyed your time. So once again, we'll be hearing from a brief presentation, and then we'll solve a challenge problem. And finally, we'll be concluding with some life lessons for girls in math and STEM. Once again, please adhere to all Zoom etiquette, but I'm sure you understand what that means now. Please make sure to participate and please ask questions. Also, if you have any final questions about the certificates, please save them for the end or direct message me. Also, we'll be sharing a feedback form soon, so we'd sincerely appreciate that you fill it out at the end. And so today we'll be hearing from Dr. Tractenberg. She's a biostatistician at Georgetown University, and she'll be focusing on variability, which is the essential feature of people, animals, cells, and systems, and the foundation of statistical analysis. She will discuss different sources of variability and draw important life lessons from her 25-year career as a biostatistician and from understanding variability itself. So let's begin.
All right, thank you very much. I want to thank all of you for sticking with this program to the bitter end. I promise to try to not be bitter. But I want to share with you some life lessons from my practice in statistics and specifically from variability, which, as Annika mentioned, is the sort of core focus and the purpose for statistical analyses. So as she mentioned, I've been doing this for a living for about 25 years. And about 25 years ago was the last time I had undergraduates, college students in my classes. And then I started teaching graduate students, and now I teach faculty. So the things that I am going to be talking to you about are hard for all of those groups of people to learn. So if I use any terms or talk about anything that you don't understand or you want to know more about, please stop me and I'll answer any questions that I can. So let's see. There's really nothing on this slide that I can elucidate. So I just want to share a little bit about what by any description is an unconventional career. It's not unconventional because I'm a woman, and it's not unconventional because I use math at work. But what's unconventional is my awareness of my role in my career and all of the different components of what makes a successful career. All of those things have been unconventional. So you can see this timeline. I do not want to know how many of you start when I got my second PhD. I don't want to know how much older than all of you I am. But what I do want to sort of direct your attention to are a couple different features of what's been going on in my life since 1988. In the last century, which is when I graduated from high school and went to college. I was pre-med. I was doing a Bachelor of Science degree, which incorporated all of the pre-med requirements of calculus, physics, and chemistry, and the anatomy and physiology that I needed so that I could go to medical school. But I also completed a Bachelor of Arts degree, which was right up my alley. I was very verbal growing up, and all my BA specific courses were in writing and communicating, and I was a straight A student. The Bachelor of Arts degree is actually in logic and analytical reasoning, and it was my ability to reason and my ability to verbalize the arguments that have driven sort of the strength of my career. If I wasn't able to explain what I am doing as a statistician, I wouldn't be as successful as a statistician as I am now. And I would certainly not be the kind of scientist that I am now. So that was a really important, lucky thing for me, that my Bachelor of Science and pre-med grades were not good enough for me to get into medical school. I had to take on another major, and that enabled me to get good grades, but it also taught me how to communicate effectively. The good thing about girls in STEM is that girls tend to be good communicators. Girls tend to be more verbal, and you absolutely have a strength if you are verbal. If you are also good in math, that's a very, very strong position to start from. So up until I was in college, I depended on my memory for everything. When I learned things, I just memorized them. It was great. So that is great for learning languages, and it's great for learning how to diagram sentences, but it's not very good for solving problems. So when I got to college, I realized that my memory wasn't good enough. I needed to learn how to learn. And between my undergraduate and my first PhD program in cognitive science, which I started in 1991, I developed a learning superpower. So I still have a pretty good memory, but now I know how to learn. When I am facing new material, I try to see what about it is hard, what can I do to help myself learn that thing? And that has been incredibly helpful for me as a statistician and a research methodologist, because every scientific field needs statistics. So when they come to me and they say, can you help me? I have to learn about what their problems are. What kinds of variables do they have? What do they need me to do? So my ability to learn is really helpful. My ability to communicate is also really helpful because I can ask good questions and I can understand their answers. So communication is really, really important to me, no matter how much math I use. The fact that I do use math and statistics is actually puts me in an office that people come to instead of me going out trying to find people to work with. So my ability to use statistics at work is really important, but it's my ability to communicate and to learn and recognize what other people need. That is how learning has become one of my superpowers. So in 1991, I started the PhD program. And in 1993, I actually was a full-time student, but I also got a full-time job at a pharmaceutical company. And I worked there for 2.5 years in the library doing literature reviews. So again, I was able to have a very good job, potentially a career. If I wanted to stop my PhD program, I could have gone into full-time library science because of the strength of my communication and literature reviewing abilities. But I continued with my PhD. I completed the master's degree in 1996. And in 1993 and until 1996, this is when I started working primarily with graduate students, teaching them to teach. By 1997, I finished that PhD program and I got a job as a scientist and a biostatistician, studying Alzheimer's disease. So I worked with physicians, and these physicians, some of them were neurologists, which is people who take care of and treat people for problems with their actual brain. So they give medication or interventions for the brain. And gerontologists who study and treat diseases of aging, or psychiatrists who treat and study behaviors and other outward signs of disease or brain damage or brain injury. So it was really very interesting, and learning about those diverse brain sciences was helped because my Bachelor of Science degree was in biopsychology. So I spent a lot of time learning about brains as an undergraduate. And then I spent 5 years applying that knowledge, learning about the specific scientific requirements of these different clinicians, and learning how to be a scientist and a statistician. But the program that I went to, my PhD, it gave me a lot of statistics. That's why they hired me as a statistician, even though my degree was not in statistics. But I realized that I didn't know as much as I should know about statistics. So I went into a master's program. It's called a Master's of Public Health, or an MPH program. The emphasis was in biometry, which is the measurement in biological systems, and biostatistics. So this, in 2002, I graduated from that program, and that's when I first really felt like a biostatistician. I had a master's degree in biostatistics. And that is when I got a job at Georgetown. So I came to Washington, D.C. in 2002 from San Diego, where I grew up in California. And I've been here ever since at Georgetown. So I started to realize the way that I had been learning up until I got to college wasn't very effective, and that learning how to learn was really important for me. But as I studied cognitive science and understanding how people think and learn, I started focusing on how graduate students learn to teach and how professors learn to teach. And I learned to teach better and how to teach other people to teach. So teaching became a superpower of mine as well. So learning was a superpower, then teaching became a superpower. And as those came together and I started working with so many other different kinds of scientists, science became a superpower of mine. I completed a doctoral certificate in gerontology, which is a demonstration of my capability to study aging and the diseases of aging. And I started a PhD program, my second PhD, in a measurement specific program. This program was very quantitative. Every course was only statistical. We learned all about different models, and all of my prior learning helped me to understand all the different things that I was learning in this new program. And I completed that in 2009. So you can see here, this blue bar shows I went to school from last century until 2009. So that's my formal schooling, but I was learning well before that. And you can see in this yellow bar, I continue to learn today. Luckily, learning is a superpower, and I don't have to go to school formally to show that I am learning or to recognize that I am learning. But I understand I need to learn new things. I am now very well able to find new things to learn them myself, and demonstrate to myself and other people that I have learned those things. So learning is definitely a superpower that you want to cultivate. Indicators of these superpowers are the PSTAT designation, which is from the American Statistical Association. It's something that you have to compose a portfolio of evidence for, and the evidence shows anyone who wants to see it that you are an accredited statistician. I was elected a fellow of the American Statistical Association, where I was recognized as a steward, a caretaker for the discipline of statistics. And then in 2017 by the American Association for the Advancement of Science as a fellow, and recognized as a steward of science. So all of these things seem like, well, you learned about SATs and you learned about math and you learned about public health and you learned about all these things, that's fine. But when they come together, and to show that science is my superpower, I show that by being the best contributor to the science that goes on at Georgetown and around the world, because I collaborate with people around the world. And these are recognition from others, independent recognition that I have in fact accomplished what I wanted to accomplish. That is an unconventional career. People usually are stewards of statistics or stewards of their scientific discipline, but not often stewards of both. So I'm trying to make this go ahead. Okay, there we go. Okay, so that's me. If you have any questions about how I managed to survive all that schooling, please ask. But now I want to talk about how I use math in my career. I talked a little bit about the fact that, when I did my bachelor's degree, when I did my first doctorate, and definitely when I did my second doctorate, it was all quantitative. There was an incredible amount of math. The field of biostatistics, or the field of statistics, it's dependent on mathematics, but also probability. And probability is somewhat dependent on math as well. But alone, math doesn't do what biostatistics does. And probability alone doesn't do what biostatistics does. Biostatistics is a discipline that takes probability and takes mathematics and puts them together, applies them in very specific ways to enable science. Now, regular statistics, if you're not a biostatistician, math and probability come together to enable other things, decision-making or policy or other machine learning or artificial intelligence applications. But in biostatistics, which is my domain, everything that I do that's statistical is based on some kind of math. I do not do the math. Software does the math for me, but I need to know how the math happens in order to understand what comes out of my software. we're going to talk a little bit about that. That's the core of what we're going to be talking about today. But probability is something that is totally dependent on math, but it's an application of math. Both math and probability, they always work. The formulas do what they say they're going to do. And the challenge is to make sure that the data that go into the formulas have the right format for interpretable results, but the formulas always work. So again, it's really important to be a good learner and to be able to communicate and understand how people are communicating with you, whether they're using equations or the results of those equations. So you can see in this picture that the scientific domain sort of only crosses through half of biostatistics, because some people can have a whole career just doing statistical methodology, just developing new estimators, improving precision, creating data wrangling machinery that serves scientists, but they do not communicate with scientists. I am in this lower half where I use statistics to do my work, and then part of my work may be to create new statistical methods so other scientists can do their work. You may have heard of descriptive statistics or inferential statistics. Descriptive statistics is what we're going to talk about today, but scientists want to describe what's going on in the world or in their data. So descriptive statistics is really important, and that's what we're going to be talking about. But the two ideas that we're going to be talking about today underlie all inferential statistics, which is where you take a sample. Instead of seeing every single member of the population, you just take a sample, like the census, which happened last year. You may have remembered or heard about that in the news. You take a sample when you can't get every single member of the population, and you try to draw inferences about that population from your sample. So instead of seeing every single person in the United States and asking them what their job is, how many people live in their household, and all of the other questions on the census, they take a sample of people in the United States, and then they say, well, there are 2,000 houses in this neighborhood. We sampled 100 of them. We infer there are 1,700 cats in this neighborhood of 2,000 homes. They make inferences based on the smaller subset or sample of the population that they're interested in. So inferential statistics rely on what we're going to be talking about, variance and means. And if you don't understand the relationship between these descriptors of your data, descriptive statistics, and the potential to draw conclusions or inferences from your data, you won't be able to design a good experiment. You won't be able to pose a good, meaningful research question. And in some cases, you won't be able to make a good decision. So statistics and biostatistics are really important for science to go forward. And some scientists choose to completely ignore statistics and call someone like me. And some people work with people like me really carefully so that the science can be as sound as possible. So some people may say that no one needs statistics because there's math and probability. But as you saw in my figure, biostatistics arises from the application of math and probability together. And one thing that people tend to attribute more to statistics than math, sometimes people talk about probability in terms of graphs. But if you have a collection of observations, a collection of data, you can make a graph and look at what the graph is trying to tell you about the data you've collected. The problem set that I sent that you may have seen already has a bunch of graphs that we are going to look at and talk about. You don't necessarily need to compute anything in order to draw some conclusions about the data that you have. And what we're going to be doing today is really leaning into our verbal abilities as women, which we tend to have. Female humans tend to be better at language than male humans. So we're going to lean into that and consider how we can explore and describe these graphs using the concepts, this numeric description that is called the mean or the variance. So you can describe a collection of data numerically, and every collection of data can be described this way. Like I said before, the formula will always work, but that doesn't mean that the formula is going to give you an answer that you can use or understand. So you can describe any collection of data with the mean or the expected value. And you can also describe it with variance. There are some distributions, some collections of data where the mean is equal to the variance, and some where there is no variance, and the mean is the value, the only value in the collection. So you can describe the central tendency or the location of your data points. You can describe the spread or the dispersion of the data points. And you do these with predictable, consistent equations. One is the equation for the mean, which we're about to see, and one is the equation for the variance, which we're going to be spending most of our time talking about. Graphs are really interesting because they tell you a lot about the data that you've collected, but they're hard to compare. And you'll see that because we're going to be looking at a bunch of graphs. They're hard to compare, but interesting to examine and consider. The numeric summary, a mean or a variance, can be compared. So even if you have the mean of one graph and the mean of a completely different graph with totally different characteristics, you can actually compare the numeric summary. Instead of saying this one looks wider, a wider dispersion than this one, you can actually compute the numeric summary and compare the numeric summaries. So in a sense, what math brings to data, which are, could be completely random, but what math brings is a bit of predictability and consistency so that you can summarize something wildly divergent and compare it to something else that is very, very different. But you can compare this particular characteristic, the mean or the variance. So we're talking about data. Data could be any observation, anything that you have collected. So observations, it could be values, it could be ages, it could be outcomes. Like I flipped a coin, one outcome is heads. I flipped the coin again, the outcome is tails. Any observation that you can think of, each datum has to come from the same mechanism. So flipping a coin would create a collection of coin flip outcomes. Tossing a die or tossing two die creates another type of data or outcomes. And whenever you collect these outcomes together or these data together, you have a distribution. In this sense, we would you consider a description of your collection of data as a summary. Otherwise, you have to say, well, variable outcome 1 was 7, outcome 2 was 12, outcome 3 was 2. So you would either just say every single one of them, or you can summarize them. That's what we're going to be talking about. So I have a question for you, and we're going to do some, I don't know if you've done this before in your gem hunt this week, but what we're going to do is, let's see, do I have the ability to see chat?
Yes, you should. You should have the ability.
Okay. So okay, yep, I see it. Okay. So here's what we want to do. Okay. Now I see the chat. Okay. Amen. You want to be a neurologist when you grow up? You should see me after class. Okay. So we're going to do something called a chat fall. Have you guys done this before? I'm going to ask you a question. Actually, the question's on the board. I'm going to ask you this question, but don't put it in the chat. You're going to type it, but don't hit return. So I want everyone, okay, Stella wants to be a neurosurgeon. I can probably connect you to some neurosurgeons if you want. Okay, so I'm going to ask you what outcomes would happen if I have 2 dice and I throw them and I count the number of dots that I see. I want you to type your answer, but don't hit return. Type your answer into the chat. I'm going to count to 20. But if you have a question, put it in the chat. But does everybody know what I'm talking about? You throw 2 die. You throw 2 dice and you count the number of dots. I want you to just imagine what one outcome would be. Neurolock. I definitely know somebody to connect you with, Ayusha. Yes, the total. Count the number of dots. So in your brain, this is called a thought experiment. So I want you to imagine you take 2 dice, throw them, count the number of dots that are showing, think about that number for the total, and type it, but don't hit return. Now hit return. Okay, that was awesome. I want you to scroll through the chat. Scroll through the chat. Okay, not 21. Okay, so this is really fantastic. We see a lot of 8, 6, 12, 5, 12, 7, 9. Now, all of those are completely valid. If you throw a dice, if you throw 2 dice, this is what you could see. This actually tells you, let's say we don't have 100 people here, but let's say each one of you threw 2 dice twice, and we have 100 observations. And I'm sorry, this is such a terrible picture, but this is the one that I had in my slide. If the first die comes up with 1 dot and the second die comes up with 1 dot, your observation is 2. If it's the first one is 1 and the second one is 2, your observation is 3, right? So this table tells you what could possibly happen if you threw 2 die, what would happen. It doesn't sum the dots, it just tells you what could happen. What you can see here is the smallest observation has to be 2, because the littlest thing you can get here is 1 and 1, so the sum is 2. You can't get a 1. And the biggest observation has to be 6 and 6, which is 12. So that's why 21 isn't right, because you can't get a value higher than 12 when you throw 2 6-sided. I should have specified their 6-sided die and not, Dungeons and Dragons crazy die. So this is what could be in the distribution. And we know from this table that the only possible outcomes range from 2 to 12. Now, here's what happens. One time I did throw 100 2 dice tosses. This is what I saw. Now, this is 100, there's 100 values in this table, and you can see the green values. The greens are times that 12 turned up, only 3 times. And 2 turned up only 3 times. That's 3 out of 100 times. That is really not very often. These are extremes. The minimum and the maximum are extremes. And it turns out, if you look at this table, well, this table doesn't show it, but 3 and 4 is 7, 4 and 3 is 7, 5 and 2 is 7, 2 and 5 are 7. There's a lot of different ways to get a 7. Not a lot of ways to get a 2 and not a lot of ways to get a 1. And that is how those end up being extreme values. And because they are extreme, they tend to be more rare. If they are not rare, they may be at the maximum and the minimum values, but they're not extremes. They're just the end points of the range. So if everything happened the same number of times in this, you would have seen 12 outcomes. Each one would have happened about 10 times, and there would be no outliers. But when they're rare, like 3 times per 100, that's considered an outlier. Now here is a picture of this is what happened in sequence. So, oh, I'm sorry. So Autumn, you have a question? Okay, I don't know how to call on you.
So my question is, like you said, like the outliers don't have to be the like the minimum and the maximum, right?
Well, typically the minimum and the maximum are the extremes. If they are extreme, they're outliers, but sometimes 12 or 7 or whatever is rare. Maybe it's a hard thing to get, but it's in the middle of the distribution. Then it's an outlier because it's so rare, but it's in the middle of the distribution. So it depends on how often it can turn up.
What would it look like? Like, I'm having a hard time like visualizing it.
Well, so this is what happened over time, and you can see the minimum and the maximum actually did that. That's what we expected, was that 12 can only happen a few different ways, and 2 can one different way, and 2 can only happen one way, and every other outcome can happen a lot of different ways. But the thing that you can see here is every time you throw, it's the same thing. I have 2 dice in my hand. I throw them on the ground. I count the number of dots. There's really no way to know what's going to turn up. It could be anything. It's only 12 and 2 a few times. So it could be anything, but if I were going to guess, I wouldn't guess 2. That is a possible outcome. But if I was going to guess, I wouldn't guess 2. I would guess something that's, more likely. And this is what's called a histogram, also a frequency distribution. So Autumn, this might answer your question. I took this data. This is what happened in real time. This is first there was a 3, then there was a 10, then there was an 11, then there was a 5. So that's here. Here's a 3, then a 10, then 11, then a 5. But when I say, how many times did I see 10 in that 100? How many times did I see 3 in that 100? This, you get a frequency distribution or a histogram. And here you can see, as you might have predicted, 7, you can have 2 and 5, or 5 and 2, or 3 and 4, or 4 and 3, or 6 and 1, or 1 and 6. There's a lot of different ways to get a 7. So, as you might have expected, that was observed the most frequently. 2 was observed the least frequently, as equally infrequent as 12. That's what makes those outliers, because there's so few ways to get them. They're so rare. It's hard to expect that that would come up. So now, if I was going to ask you, let's see, move this picture of our. I'm trying to move our the picture of all of you. Okay, so I want to ask you all a question. If I ask you now, oh, awesome, Rowan, that's great news. So if I ask you now, picture in your mind, you're going to throw 2 dice. What is the sum that you expect to see? What would you say? So I want you to type that into the chat. You throw 2 dice. Yeah, 7. Right. It's you have no idea what's going to happen, right? Because as we saw, it could be anything in this range. And in fact, look at how long it took to get a 7. 1, 2, 3, 4, 5, 6, 7 tosses before the first 7 got thrown. So it wasn't the first one. The first one was a 3, which is pretty rare, but that's actually the first thing that happened was a 3. And then you had something else rare, 10. There's only 2 ways to get a 10, or 4 ways to get a 10. In 11, there's fewer ways to get. So rare things happened first, and then a 7 happened. But if you had to guess, and you only had one guess, you would guess the most frequently occurring outcome, and that is the origin of the expected value. So what you should be paying attention to here is there's variability. When you throw the dice, you do not know what's going to happen because the outcome can vary. So variability happens, and the field of statistics exists because variability happens. So if everything was the same, then I would say, well, everyone was a girl, or it was always a 7, or I gave lemons to sailors on a sailing ship, and every single one of them who had scurvy got cured. That's actually the first clinical trial that was ever done, was to cure sailors in the 1700s from scurvy. If not everyone was cured, then there's variability. Some people got better, some people didn't. If you've ever heard the expression, take 2 aspirin and call me in the morning, that's a very old-fashioned expression because people don't take aspirin anymore. Take 2 Advil and call me in the morning. If you have a headache and you take 2 Advil, there's no guarantee that it's going to make your headache go away. Your headache may just go away because time passes. So there's variability even in things like aspirin or Advil treating pain. These things always vary because human beings vary. Even if you have something like totally cured, mostly cured, kind of cured, and not cured at all as potential outcomes, there's going to be even more variability than if you just had cured and not cured. So you can create more variability, and you can restrict how much variability. So you would say cured, mostly cured is one option, mostly cured, kind of cured, and not cured are the other options. So you can reduce the variability or increase the variability in your sample, depending on how you ask the question. So humans have variability, weather has variability, organisms have variability, even clones. This, you might be surprised, even clones are variable. And here is an example. So again, I apologize for my terrible visuals, but this is data that was collected in a study that I was involved in. So you can see this is about mice. And if you remember from my educational trajectory, I did not study mice at all. And this is the mouse's heart rate being measured over 8 days. So I didn't study cardiovascular or anything or cardiac such and such, but because I'm a research methodologist, these people who were doing mouse models of hypertension called me. I learned about their model, I learned about their system, and I applied my statistical expertise to their problem, and we came out with this particular problem. So you can see here, these mice are all genetically identical. They were created in a lab. So at this point, we just woke them up and said, you know, it's 8 o'clock in the morning, mouse, how are you? We took a heart rate measurement, and then we gave them a pill, and then these clones diverged. Now you can see everybody had some reaction at time 1, but some reacted very little and some reacted very dramatically. They're identical. And then when time is passing, they're even more variable. Then when you break them apart and you say, okay, these XX mice are girls. Emma, I can't explain how they cloned the mice, but because that's not my field, the lady told me they're clones. It's a litter of mice and they're genetically identical. I'm not really sure how they clone them, but it's something that's systematically done. So it's not a secret. And every time they want to clone these mice, they can do it. And they follow the same sort of recipe. Yeah, it's very cool. Okay, so you can see that the XX mice, these are girl mice, and the XY mice are boy mice. You can see that the girl mice have a highly variable response on day 1. And then they all group together, except for this blue guy, number 13, this blue girl, number 13. But their variability in the girls tends to be focused on their initial response, whereas the boys just go crazy. So they get their first, whatever, their pill, and then they're just all over the map. So when you look at this variability right here, if you limited it to only girl mice, you would have much less variability. If you looked at only boy mice, you would have crazy variability. When you look at them together, you have crazy variability, and it's driven by the boys, the boy mice. So what's important here is there's variability even for clones. Variability is critical. And like I said before, you can see more variability if you separate out like girls from boys, maybe. Yeah, the girl mice are all, everybody's a clone except whether or not you have X and Y. Yeah, 13 would be an outlier, Alicia. Awesome observation. But I want to point out how 13 is an outlier. Not because they're so extreme, they don't really change at all. If you see 13's line, she's just tootling along. She doesn't really change at all. Everybody else has a reaction and then bounces back to better than before. 13's like, meh, and then whatever. So 13 is really not affected at all. Whereas if you look at the boys, there aren't any lines in the boys' plot that looks like number 13, the girl. She is an outlier because she's just doing something different, which is fantastic. When we looked at the possible outcomes of the rows of dice, you can see you can't get smaller than 2, you can't get bigger than 12. We don't know how these mice or mouse cardiovasculature would change when we gave them this pill. We did not know what would happen. So 13 is one extreme. She's like the minimum amount of response, really. And that's a fascinating new tidbit of information that we know. If we are giving a drug, for example, we're developing a drug for improving heart function. Number 13 is a person who is unlikely to respond. Now, she's a clone of all the other mice in the girl pile. So what is it about her that makes her non-responsive? Maybe she has one blue eye and one green eye. I actually do not know, because obviously I don't understand cloning, but there's something about number 13 that's really, really informative. And she, number 13, changes the way we think about this intervention. We have to consider people who will not respond at all when we give them this drug. So she changes the way we think about how we're going to design a clinical trial. We need to make sure there are people like 13 in the study so that we captured their contribution to the variability of response. So something like this, I said earlier, graphs are really interesting to describe, but it's very difficult to summarize. It's very difficult to compare, but you can still get important information when you look at the data this way. So clones vary, everybody varies. Yes, they all have the same environment. Ahmed is asking, if something's endangered, can you clone the living ones to produce more of that endangered thing? That is a question that we should totally talk about, but we won't have time to do it today. I think the problem with cloning new ones is their genetic makeup becomes more variable and more fragile and less predictable. If you have natural reproduction, it's much more likely that you have a richer gene pool and less likely to have inbred deficiencies. But when you clone, you basically create these circumstances where genetic deficiencies and problems that make it hard for these animals to stay alive and have a normal life, that becomes more problematic. So we can talk about that. Be sure, Ahmed, ask again at the end if you have another question. Okay. So yes, they all have the same environment. The girls were cloned together and the boys were cloned together. So they were everything cloned except for their X and Y. Outlier in the boy mice. Yeah, you definitely don't want blood issues like hemophilia and albinism. And Autumn is asking about the, yeah, this green one kind of looks like the blue, number 2 kind of looks like green, but he's up in the mix. He's not like down below everyone. So if you took one green and one blue and put them together, it would be 13 and 2, a girl and a boy. But if you look at the boys together, there isn't really anyone who stands out the way number 13 stands out of the girl pile. Okay, we're gonna move on to some math. Okay, so now we can't actually do it with these plots, but we can do it with this kind of plot, a histogram, to talk about, to compute a numeric description. Numeric descriptions help us understand variability. Now, that is not true for plots like this. We can talk a completely other time about how to summarize data like this. Actually, I wrote a paper about how to summarize variability like this, but we're going to talk about histogram type of distributions instead, because they're much more common. So you need at least one numeric descriptor whenever you talk about a distribution. And this is actually called a moment or arithmetic moment. So every distribution can be described with its central tendency or measure of location. And the most important one for statistics and comparison purposes is the mean. You can also use the median, which is the number that 50% of the values are below. And of course, 50% are then going to be above. And you can use the mode, which is the most frequently occurring value. But modes and medians are not as arithmetically well behaved. They don't enter into the mathematical functions involved in statistics and comparisons very well. They don't play well with others. So the vast majority of statistical analyses focus on means. There are some that focus on the median, but they require a lot more information to draw a firm conclusion. Now, if you need to describe central tendency, instead of just saying everybody was a girl, or I flipped the coin and it turned heads, if there's variability, if you have to describe the central tendency, then there must be variability. And This brings us to our first life lesson. If there's no variability, then having an average value is completely meaningless. There's no point in talking about the average when every single value is the same. Variability is what makes life interesting. Otherwise, it's just all the same. So without variation, the idea of the average is meaningless. But it's also true that the mean or the expected value, it's not very representative of all the data. So here you can see that the average or expected value is going to be 7, but it clearly does not explain, it doesn't describe every value in this distribution because there's variability. So it's really important to know that you can always compute the mean, but it isn't necessarily going to be descriptive of all of the values. So it does have its role, but it doesn't do everything. The summary of the values requires a description of the dispersion as well, so you know how well the mean describes the collection. So that's a really important thing to keep in mind about the mean. Like I said, the equation is always going to work, but it isn't necessarily going to give you the answer that you want. So that's really important to know. Then, thinking more broadly, it's okay if you don't fit the expected value. You may still be in the distribution, you may be an outlier, or you may be in a completely other distribution. That's all fine. It's absolutely okay if you are far from average, if you are far from the expected value or different from the expected value. That's absolutely fine. Everything varies. People vary, clones vary, everything varies. It's okay to be in a different distribution or at the very high end or the very low end. It's absolutely fine. One of the most important things to know about you and the distribution you fall in is, do you want to be average? Do you want to be better than average? Where are you and where do you want to be? And what do you need in order to get there? Do you want to get out of the distribution you're in and into a different distribution? You absolutely need to recognize where you are in order to get out of the distribution you're in. Otherwise, you're just doing random things. Okay, so we're going to move on past this and look at some math. Okay, so I can't remember who was saying they were doing histograms today in their algebra class, but I'm sure you will tell me. So you may have seen that when you were looking at histograms in class. Oh, Rowan, that's right. Okay. So did you see this formula today, or when you were talking about histograms, Rowan? Did you talk about the mean? The mean is the average value. It is the average of all the values. So you've collected, you saw we have 100 sum of dice values. So they range from 2 to 12. We have 100 of those values. You saw them in one of the tables. So in this example, n is 100. We have 100 observations, and x is the individual observation. This is the mean formula in the ith place. So the first observation you saw was 5, or 3. Right, okay. So you're gonna, Rowan, you're gonna be ahead of the curve here. Haha, no pun intended. So if you've ever seen this, this is the sigma means to sum. I is counting from I equals 1 to I equals n, which is 100 in this case. Yeah, that's right. Add all the numbers in the data and divide by the number of numbers. Absolutely right. So n is the number of numbers, the number of observations. Here is x where I is 1, x where I is 2, and you add them up until you get to the n, x. Now, this is what you would call an abstract representation of the formula that Amen just described. All you have to do is add all the numbers in the data. That's this right here, sum, as I runs from 1 to n over xi. That's summing all the numbers in the data and divide by the number of numbers. That's this. So this formula is verbally described the way Amen has described it in the chat. So that's absolutely true. When you do that, you have something called X bar, which is the sample average. You've collected all the values in your data, that's a sample. And when you compute its mean, you call that X bar. Bar means bar means average, and X bar is how we describe the average value from a sample. Now, I told you about inferential statistics is where you think, what is everyone in the entire world, every possible throw of 2 dice, and I counted the dots, which is infinite, obviously. The true mean there would be mu. The population mean is called mu, but we estimate it with X bar based on our sample. X bar, the sample mean, is also called the expected value. Yeah, mu and stat bar. So if it's Greek, mu, sigma. If it's Greek, it's population. If it's sample, it's just regular letters. That's how I remembered it. Okay, so now we talked a little bit about outliers. We talked about number 13, the girl, and the blue number 2, the green boy in our clone example. They're outliers. Now, if I took the 100 observations that we saw, here they are. There's no outlier. I put them on the same axes so you can see the comparison of what happens when you get an outlier. The mean that I computed for those 100 observations was 7. But when I add just one value, so this is 1 out of 100, 99 of the values are between 2 and 10. That check, 2 and 12. And one value comes in at 48. So, of course, that's an impossible value in a 2 dice dot counting exercise. But this is an example where the mean is 8, which, you know, it's not that far off of 7, but it's 1 whole point higher. When you're only looking at a range from 2 to 12, 1 whole point is actually, you know, 1/12 of the 1/12 of the range higher. But it doesn't describe this point at all, because this point is 48. So you computed the mean, the formula absolutely worked, but it doesn't describe every value in the distribution. And this is a picture of that. So this guy out here, 48, he is an outlier. If you saw this kind of outlier in your data, and you know that it should have been no higher than 12, you should check to see that 48 isn't actually the 2 die. One came out 4 and one came out 8. Maybe there was an error in entering the data. The mean tells you where the most likely value is going to be, but outliers can affect what is expected. And that brings us to our next life lesson, which is outliers for the win. It's okay to be as far from the mean as you are in any distribution. Aiming for the expected means you're aiming to be average. And I mean, that can work just to get stuff done, but you should never limit yourself to what's expected, because you can be a fantastic outlier. There are so many other interesting values in any distribution. And if you don't look at what's expected and challenge it, then change can never happen. So if you think about our conversation about blue number 2 and green number, blue number 13 and green number 2, those mice challenge our expectations because they're outliers. They're different and they make us think harder. And if we hadn't seen them, they may still be operating in the background, but we would never be aware of it. So our research is strengthened and the world is strengthened when we focus on what we can change, and being an outlier can be how you make that change happen. Bye, Alice. Thank you. Okay. So you have your mean. It describes where most of the data are, but you do also need to consider spread. You can think about range between the lowest and the highest. You can talk about quantiles, or you can talk about variance. And this is what we're going to keep spending the rest of our time talking about, is variance. It's a single value summary, just like a mean. It's an average, just like the mean. But what it tells you is, on average, how far away from the sample mean is each individual observation. You square it because you don't want too many negatives and too many positives. They cancel out and make 0. So you have to square every difference so that you can see the absolute value of the difference. And you do that by squaring it. And you sum those up and divide by one fewer than the number of data points. So in fact, the variance is an average, just like the average is. You may have heard of the standard deviation. It's the square root of the variance. It's just easier to talk about things that are not squared. So the standard deviation is how many units away from the mean, and the squared is how many squared units away from the mean. So it's more conceptually simple to understand standard deviation, but you can see that the formula for the variance and Annika, this is the sample variance because it's just a regular letter, not a Greek letter. Okay, so life lesson 3, if, let's see, Alice is gonna miss this. This is the last life lesson. It's really important to recognize and own how you differ from the expected value. You worrying about how you're different isn't helpful, but recognizing how you're different and understanding if it's a real difference, a meaningful difference, or not meaningful at all, not worth bothering with at all. That's really, really important. It's a life skill. And knowing that everybody varies and everything varies, and you may wake up this morning and want eggs and wake up that morning and want fruit. Everyone is variable. If you see where you are and how that differs from where you want to be, that's the only way to make a plan to change where you are in a purposeful, purpose-driven way. So the upshot, if you leave now, is variation is natural, and what's expected is literally the average. Varying from what's expected is how expectations are challenged and change happens. And women, especially your generation of women, are going to change the world. We need to challenge what's expected of us and make real change happen. Speaking of change, here is an image from, you can see at the bottom, this is the New York Times has partnered with the American Statistical Association to do a program called What's Going On in This Graph. So you can go to any of these URLs or you can Google what's going on in this graph, excuse me, and you will find 80 or 120 different graphs with different challenge questions on it, like I did. So what this picture shows is what day of what month did the first plant, the first springtime growth happen? So they took values from Florida, Georgia, Kentucky. Every one of these states contributed a data point, and they represented that in this way. You can see that the variation is over 5 months. There's 5 months of variability shown in this picture. There's a huge amount of variability, but it's the exact same event. First springtime flower. So just because it seems like there's going to be some consistency, that doesn't necessarily mean there will be. And you can see that it's not just, there's almost no variability is almost all north to south, but there is a little bit of variability east to west, especially when you think about topography. So the Rockies create variability. And when you think about the mice and why they varied in their response to that pill, maybe some of them have some kind of Rockies in their system, something that even though they're genetic clones, they just react differently to different drugs. This is another temperature related graph, but this one shows differences. So you can summarize. Okay, so Amin says your differences make you unique. That is 100% true. So this graph is showing deviations from the mean. The mean was computed during this period. So you can see these values are deviations from this period's mean. So this, in 1880, when they started this survey, there was a negative, I don't know, 0.25 degrees centigrade lower. So these temperatures tended to be lower until about 1940. They tended to be lower than they were between 1951 to 1980. It's a 30-year period. And after that period, they tended to be higher. They're actually much higher on the high end compared to the middle than they were lower on the low end. So when you look at this, it kind of reminds me of the boy mice and the girl mice, where the cold temperatures were a little bit colder than they were between 1950 and 1981, but the hot temperatures were a lot hotter. There's a lot more variability, and the deviations from the average we're interested in are greater. So you can see, you wouldn't want to describe the average temperature for this period. That wouldn't make sense, because these are all negative and these are all positive. So the net change is going to be 0, because when you look at the average over some positive and some negative, even when you take the average, it will probably be 0. But if you did the variance, because you're squaring, you would get a lot of difference here and even more difference here, and the values would be much greater. Okay, let's see. Okay, now here's something that is similar to what we are talking about, why we are meeting virtually, is the coronavirus. This is variability around estimates. So what we were looking at with the dice is the mean value that was observed, and in the temperatures, the mean value that was observed. But here we're trying to predict how many people are going to be infected by each person with coronavirus. That's on the x-axis. On the y-axis, it's how many of the people who are infected are going to die, the fatality rate. And you can see that instead of a dot, like you see for smallpox, that is a very precise estimate. So more than 50 people don't die who get smallpox, but less than 50 people don't die when they get smallpox. It's about 50 people who die for every person who gets smallpox. And when you look at the x-axis, it's how many people are infected. So roughly 3.5 people are infected for every 1 person who has polio, and 8 people are infected for every 1 person who has chickenpox. There's not a lot of variability around those estimates, but for coronavirus in February of 2020, we did not know. It could have been like swine flu, or it could have been like polio in terms of the infectiousness, that's the x-axis, but it could have been like seasonal flu, or almost as bad as SARS in terms of fatality rate. So there's a lot more variability in the estimate of fatality than there was in the estimate of infectiousness. So what this plot shows is the amount of variability in one dimension was much greater than the amount of variability in the other. Both were variable. We did not know how much fatality or precision would be. And this is the final example, which is errors in predicting rainfall. So here you can see that 0 days away, so today I want to predict how much rain there's going to fall. There's not a lot of error. These people are pretty good at predicting how much rain will be on the day of raining. But 9 days from now, which is the bottom, they were not very good at predicting how much rain it would be 9 days from now. And that was true whether they made the prediction in September, October, November, or December. So you can see there are trends here. 0 days away didn't really matter until you got to November. In November, errors tended to spike for some reason, but then they went back to low. But the further out you try to predict, you can see that predictions are less precise. Errors get bigger. So variability is also variable. And that's an informative result. The formulas always work, but it doesn't necessarily end up with, it doesn't necessarily give you a single answer or the answer that you were after. Okay, so now what we're going to do is talk about the graphs that were in your problem set. So Annika, do you want to describe what we're going to do?
Sure. So does everyone have their workbook, or do we need to link that in the chat? Actually, you know what? I may as well do that.
Okay.
Mhm.
So I've come up, okay, so a couple people don't have it. So what I've come up with are 4 additional plots. I want you to get, let's look at this one. I want you to get as far as you can get. You can start with the first plot in the set or the last plot in the set in your group, whichever you want to do. But what you're going to do is look at the plot and describe the signal of variability. What about the plot that you're looking at is variable? You may also see some constancy, something that's consistent. So you can talk about that as well. Like there was surprisingly little variability in this plot, or there was a dramatic amount of variability in this plot, or whatever. So you have 4 plots, and what you're going to do is craft 1, or 2 sentences describing the variability. What is varying? How badly or well does the variability just help you understand what's going on in the plot? But all you're doing is linking your strong verbal abilities to what you understand about variability, given what we talked about, and come up with something that you can communicate to another person. That's what you're going to do in your groups. And then we're going to come back and you're going to describe your plots to each other.
All right. So if everyone doesn't have any questions before we go into our breakout groups, I will get everyone going. We have 15 minutes. I scheduled 15 minutes. And Anika, if you could just let me know about with a minute left, whether or not they need more time, that would be helpful. So when you're visiting the room, just either shoot me a message or something like that.
Yep, I'll let you know.
All right, let me make sure everyone's in a room. Okay, we have add, and then, sorry, sign. I know some people are coming in and out, so I just want to make sure I got everyone assigned a room. All right, we're all set, I believe. So here we go. Candace and Anika, I didn't put you guys in rooms.
Yeah.
We have 5 rooms today.
Mhm. Yeah, you know, I think because it's Friday, a couple of people, you know, decided to
Yeah,
skip.
let's have a good amount though.
Yeah, for sure. Okay, well, I'm gonna start with room 1. Candace, if you want to do any of the other ones.
Yeah, I'll go to room 3.
Okay, sounds good.
All right, and Laura, are you having problems getting into a room? Maybe. You have to just hit the join button sometimes. Maybe not. Sometimes they join from multiple devices, you know, so. There we go. All right, so now it's just you and I.
So I think I went over time.
That's okay. Sometimes it needs more, instruction, more understanding. So
Well, I think they asked great questions, so that was just awesome.
yeah, I mean, the girls have been really great this week. So we're really pleased with everyone's doing, their part of engagement and yeah, again, it is Friday
Yes.
after a full day of a full week of a lot of these kids are on still full-time Zoom,
Right, yes.
so
Well,
for
so,
them.
my original plan was to have life lessons at the end, but I figured it's 5 o'clock on a Friday. And, if I am hankering for a margarita, I'm sure the kids are also, or whatever,
Yeah,
all
whatever
the
they're
11-year-olds do for margarita worthy activities on a Friday. But anyway,
yeah, exactly.
yeah. So so I wanted to make sure that they got in, because that's the really most important part about
Yeah, I think that is, especially when you're talking about, where do you want to sit on the graph, personally
yeah.
as a person, right? So
Yeah. I mean, I hope, it seems like they communicate with each other on the chat as well. Are they like cheering each other on and being supportive?
yeah, it's so funny because I've popped into a few of the breakouts because they've asked for help. The math on the first couple days was
Yeah.
really above.
Crazy.
Yeah. I mean, they're like, well, we designed it for graduate students. I was like, well, they're middle school.
Yeah, my graduate students I saw the problems and I was like, wow. I wouldn't even give my graduate students these word problems, actually.
Right. So yeah. So yesterday went a little better because it was a little more subdued math. It was more just multiplication. So they were good. But definitely the first couple of days I'd walk into a room and it would just be dead silence. And I was, and they're like, we don't even know where to start. I'm like,
yes.
Okay.
Yeah.
So-
So I pinged Anka to see how it was going, because when I saw those problems, I thought, I mean, I work with instructors.
Yeah.
So I know how hard it is to sort of teach math.
Right.
And I know that a lot of instructors struggle, but aiming your graduate student materials for 11-year-olds is incredibly complex. So
Right.
I anticipated that there might be some dead.
Yeah, there was some dead air. This is my dog. That's
Oh.
just decided to.
What kind of dog is that?
It's a Cavalier, King Charles.
Oh, wow.
I'll do my non. She's very upset right now because
Dinner time.
no, my husband just left with my son.
Uh-oh.
They're going down to Virginia Tech, like as I
Oh,
mentioned,
right.
for a visit. So, I was just sending them off, and she's all upset because of course he just got home and the husband did, and she's like, what do you mean he's leaving right away? So she's very like, this is not out of normal pattern.
Hey.
The variance here is not very, like, you just changed my schedule, basically.
Yeah, that's unacceptable.
Yeah.
Well, my two are blocked out with daddy watching television. So they're when I open the door, in fact, usually they will cry at the gate, which is down the hall, so that you don't hear it. But Mommy, what are you doing in there? Mommy, are you okay?
Yeah.
Mommy, I need to see you. I need to check on you.
Yeah.
They hate closed doors, and it's just so worrisome. But this is actually the first local meeting I've been to all year. They've been like international, they've been, whatever. So like really not high stakes, but
this is, I get it. We're not exactly, saving the world problems here. So,
but not
not yet. These girls aren't yet, but they may soon. Who knows?
That's right. That's right.
They want to be neurosciences.
Well, one wants to be a neurosurgeon, one wants to be a neurologist. So we might have a little Zoom group just on that. But my mom was taught 3rd, 4th, and 5th grade for 35 years. She teaches elementary school, teachers now. Oh, and high school teachers. So she's a master teacher now. That she's retired at. My sister had 7th grade boy and a 7th grade girl. So I told them I was giving this talk, and they were like, A, oh my God, don't kill those children. And B, it's so important that I told them what my message, my life lessons were, and they were like, oh, it's so important. And they were talking all about how, one wrong word from me and these kids are going to be drug addicts for the rest of their lives. And no
I certainly hope
pressure,
that's not the case.
no pressure, but don't mess these kids up. Don't make them not want to be scientists. So
Yeah.
I'll be very happy to report all the great questions about who wants to be a neurosurgeon and how they are educating me about cloning.
Yeah. Well, they're boys and girls, so they can't be from the same. I was like, whoa.
That's right. Wait,
Like,
what?
I didn't even think about it. I just
either.
assumed. Yeah.
What's so funny is, I pride myself on being able to spot what the scientist does that's going to mess up my analysis. And obviously the boys and the girls were going to be compared. That's why they're in a
Right.
sample.
They're in one group versus
Yeah.
another group. You're right.
No, they're going to be compared to each other, boys versus girls, but it's one cohort. So they are all born on March 1st and whatever. So so the XX versus YY would be compared. But when I did this study where these graphs come from, I separated them because the graphs look different, not because the girls were clones and the boys were clones. I just put them all in the pile together because that's what the modeling says. The modeling says they should all have individual intercepts, or they should all have individual slopes, or both. And I didn't think about that when I was making these graphs. So
Yeah,
I thought they
I
could just
didn't
say
either.
clones differ. What? That's amazing. Next.
You're like, okay, we're gonna move on.
Wait, when you say clones,
Yeah. Like, how were they cloned? Were
how
they in a
exactly were they cloned?
yeah.
And, I know how did you clone the mice was Emma's question. I know that these particular animals were cloned and cared for under the current animal protection context. So this is only 10 years old. So these animals were very carefully cared for. Whereas 11 or 12 years ago, I would not be very confident about that. So at least I know that they were.
At least you walked into it feeling a little more confident about the quality of the care that the animals were receiving.
Absolutely. Well, it's
how they were created. Yeah.
Well, I don't know if you saw this, but someone says if a species is becoming endangered, you can clone the living ones to make more.
You get into all sorts of gene pool issues. Yes.
Yeah, but I mean that's just such an interesting question. This person.
Well, it is. It's funny because here I have a Cavalier, right? So the breed itself was wheedled down to less than 20 dogs at one point. So
wow.
Unfortunately for that breed, and they have a heart murmur that develops, and they have a cardio issue was they age. A lot of them do.
Right.
And almost 100% of the dogs have it. It's the severity of which you have it, right? And so they talk about good breeding and bad breeding, right?
Yes.
And breeding out that bad.
Right. Right.
So I thought of that immediately when I thought about, these dogs all have it. It's the severity of which they have it.
Yeah, absolutely.
Based off of what the quality of the breeding that was done with the dogs.
Yeah, absolutely.
So,
I mean, our dogs are Rhodesian Ridgebacks.
Oh yeah, I know that. Yeah.
This is our second pair. The first pair was the first time we'd ever had purebred dogs, either one of us, and we were told, look at the hip, quality, the medical quality of the hip of the parents and the grandparents and the great grandparents, if you can. And the breeder, of course, has documented the crap out of all the genetic contributors to this particular litter. So she had, it's called OFHA hip analysis going back, 6 generations. So these dogs definitely not going to have hip problems because, for 6 generations, they've been making sure they don't breed dog, and no dog enters into the breeding program that has a hip problem. So it's, 6 generations, that's just nuts. But
I know. Think about 6 generations here in the United States. Like, where's that?
Actually, the 6 generations for these Ridgebacks started in Rhodesia. I mean, was called Zimbabwe at the time, but they're South African, or they're African.
They're lion hunters.
Yeah, that's right. That's right.
Yeah.
And
I have a
they're-
friend who has one.
yeah,
And her second, actually, they've had a Rhodesian now. This is her second. But that dog is so funny. I'm like, that thing would never be a lion hunter. She is like the most
that's hilarious.
timid,
Oh my
like,
God, that's so funny.
yeah, like she's like, whatever, dopey, just dopey, you know.
Yeah, mine are
Like-
definitely not like that.
No,
They're definitely like that. Okay, so
but
it's
she
five.
loves to run. Oh yeah, so where are
it's
we?
5:20.
2 minutes.
Do
I'm gonna
they
give-
come back or do you let them back?
Yep. So I set the room to 15 minutes.
Oh, okay. So,
So
it'll just
I'm gonna send a message right now. So everyone in a room will get, I'll say 2 minutes left. 2 minutes.
and
left.
then I have 6 minutes to sum up.
Yep.
I'm really sorry about that. I totally.
That's okay. Well, you can run over. It's all your time. So
Oh.
these girls, I mean, I can't tell you one day has ended at 5:30, just FYI.
Oh, good. Okay.
So if you need extra time, people will do the same thing. Like, I have to go, my dinner's ready or
Yeah.
whatever. Or I have some family obligation, but mostly they're here and they're committed.
Okay.
So,
Because I definitely don't want to keep them
I've
from.
been really, really pleased with the interactions of the
Oh,
girls.
good.
So.
Well, so I mean, this is the fun part, and I want them now. They will take their microphones off and talk.
If you encourage them to, they will. Some will, and you'll notice there's a certain grouping of girls that are more boisterous to talk. You know, so which is great. They may be older, they may be more confident, you know, that's
Mhm.
really what we try and encourage, is just keep the love of what you're doing.
Yeah, absolutely. Well,
Yeah.
definitely. I mean, so it just so happened that our first graph is a women's marathon times.
Yes. I saw that.
Yeah. So, and I tried to stay away from controversial topics, obviously.
Yeah.
But having the top 50 marathon times in any given year
Yeah.
for women, it's really quite incredible.
It is.
I don't know if these girls run, but I mean, when I was their age, I wasn't running marathons, but I was running distance. I'd already shifted from sprinting to cross country. So
Yeah, it's very interesting. Like yesterday, one of the presenters said that she played the cello, and all of a sudden it became this like
Yeah.
conversation of well, I play the flute and I play
yeah.
it was really crazy. It was great. I mean, it was, not related to anything, but like both the presenters and the students were all just interacting.
Mhm.
It was really nice.
I don't know how these kids think about. I didn't go into. I mean, I went along my continuum of education, but I didn't talk about what Am I a senior person? Do I have tenure? Obviously I'm
Yeah.
old, but is it? Am I somebody that they would ask questions of? Am I somebody that they would recognize or sort of have any kind of affinity with? So talking about dogs or cellos or whatever.
Yeah.
This person's a professor, but they like Disneyland, and so do I. So we can talk about that kind of thing.
Exactly. And and it's just finding those commonalities. I
Mhm.
mean, that's it's hard in the Zoom format these
Yes.
days. So I definitely, it's interesting because this past fall we did 5 days of this, but the year before that we did it in person.
Oh, wow.
We did but we did one day
Oh, okay.
with
All day.
with 4 breakout rooms, so to speak. And the girls did like a scavenger hunt between
Oh,
the rooms.
interesting. Uh-huh.
Yeah, so that was really fun.
Mhm.
And I think ideally, I was saying to some other professors, and I'm sure you're in that same place, is I was like, God, I would love to be able to partner with a university and schedule like a half day thing where they could come in, visit labs, and really see where where this stuff kind of comes from, so they have a better understanding, and then just encourage them to ask, different questions about, different, and it doesn't necessarily have to be just one department. It could
Right,
be
yeah.
multiple, within that world,
Yeah.
So
I
don't
think
know.
one of the difficulties is, especially for me, in biostatistics is almost never even offered to undergraduates. You have to have
Oh, it's
whatever
really
your
again,
undergraduate degree
graduate.
is, and then go into biostatistics for your master's or doctoral level training. Whereas you can get an undergraduate degree in statistics. You can't get an undergraduate degree in biostatistics. I guess because
Right.
it's applied, so you really have to understand how the stuff works so that you can apply it, I guess. But But what I do, I am a measurement expert and a trial designer. So to work with me, you have to have a master's degree or a doctorate before we can even have a conversation. You know what I mean? About like, can you come into my lab and see what I do? No. If you have a PhD and I tell you what I do, then you'd be like, oh, I think I see what you're talking about. But so I almost said no to this invitation because I wasn't sure I would be able to come up with anything compelling at all.
For this level.
Well, not for this level, but something that I could talk about for 20 minutes and then they'd be able to do.
Right.
Like, what can you do with only 20 minutes of instruction
Yeah.
that's relevant to my work that isn't tedious, like doing an equation, that's just tedious,
Right.
I don't want to.
Well, believe me, they love the problems though. They're like, is there a challenge problem today? I mean, I got that message today.
That's great.
Already. Yeah. I was like, yes, there is. Don't worry.
Yeah,
So.
I mean, I'm really looking forward to hearing what they say about the graphs. So I'm looking forward to the.
All right. Well, I'm going to go ahead. I haven't gotten anyone. So I think they're starting to come back. So I'm going to start closing out the rooms.
Yeah, I see Aklilu has joined us. And I reckon you're going to edit that entire conversation out.
Of course. No, we take out that whole section. That's the best thing about editing these days.
Yes, absolutely. That's great.
Yeah. How'd it go in there, Candace and Anika?
Pretty good. We had some really interesting discussions about like why certain things are increasing.
Awesome.
Good.
Maybe you two can help me call on people to invite them to share some thoughts about the graphs as we go along. Like who did you see having a discussion about the marathon times? Who did you see having a discussion about the different graphs? Do you know what I mean?
Yeah, sure.
I mean, it's day 5, so instead of just waiting and volunteering to call, you can call on them.
Okay. Well.
Yep. Everyone's back now. So.
Oh, okay. Okay. So thanks for coming back. Now I want to be respectful of everyone's time, and I know that we're coming up against 5:30. I have all day, but I certainly don't want to spend it doing this. No, I'm just kidding. So we're now going to talk about what you noticed and saw and talked about in terms of the variability. What is varying? Where is the variability coming from? And if there's anything consistent in the graphs, I want you to talk about that. And Anika and Candace are going to help me figure out who was talking about marathon times, which group spent a lot of time talking about this one, and where do you think we should go to hear about what is going on in this graph? Oh, Alicia?
Oh yeah, I said that like as time is progressing, the time that it takes a woman to run a marathon, like a mile in a marathon, is decreasing, and that's like consistent. Like there's like you can see like a trend line that's like showing that. Yeah.
Excellent. And Ahmed?
I think like outliers would be at the top, because there's like one woman that made a little less than 2 hours, but like it's more crowded at the bottom. And as Alicia said, the trend is like as the years pass by, women are taking less time to finish the marathon.
Yeah, absolutely. And you can absolutely see that if you turn your head and you look for any given year, there's a cluster down at the 230, which is the lowest value is 245. and the bottom of the graph is 250. My fastest marathon was 347, by the way. It was on my treadmill, so I didn't even get a record of it. But so I mean, I took a picture of my watch, of course. So but you can see everybody is grouped at the bottom, and then they sort of trail off to the outliers at the top. So everybody at the top is an outlier. Thanks for coming, Stella. Okay, and Anastasia put comments in, and so did Ayusha. That's great. And Autumn.
I was just thinking about this, but I kind of skimmed through the article. And I kind of have like a hypothesis. Like it mentioned how like the women, how like it's kind of like demographic information. From what I remember, it's like a lot of them make more than 100,000 a year.
What?
So I'm thinking, right? And I'm kind of thinking that they invested money over time and like trainers and stuff. So as you see, like they're progressively like getting faster. So
well, that's a really interesting point, because probably not a lot of you were even a thought in a parent's head in 2000, but the idea that a woman could do a faster, maybe a 2:10 or a 2:15 marathon wasn't really a marketable idea. But in about 2010, that became a much more interesting, much more lucrative idea, that somebody would pay a champion who was a woman to run a fast marathon. I hate to tell you this, but in the 70s, there was a woman, the first woman to ever run the Boston Marathon, and she was prevented. She tried to run the Boston Marathon multiple times. They prevented her because doctors thought if a woman ran a marathon, her uterus would fall out, because they didn't know anything about women's bodies or how awesome we are. But I digress. Anyway, so that's a really interesting point, Autumn. Okay, we're gonna look at the second graph. Who had some comments about the world leader age over time? Now this one has some interesting signals of consistency and variability as well. Alicia.
Yeah, I thought that like the overall trend is that world leaders are like getting younger. And like, so like Trump and Biden would be outliers because they're like towards the top while the line is moving down.
And Ayusha notes where the average is around 63, but you can see that actually changes over time. So I would say, Camilla is asking, would you say that the trend is the line of best fit? And in fact, it is the line of best fit. That's how that line comes into being. And best fit is the line that minimizes the average difference between an observation and the mean, which is the variance. So minimizing the variance with the line you draw, that's how a line of best fit is computed. Ahmed?
Yeah, Ken, like Ayusha just said, I was about to say that, but Kennedy was also like an outlier because he's not part of the trend. Like it was near 2010, 2020 that like the world leaders overall like on average got like were younger, but Kennedy in the 1960s, he was very young. And like at that time, most of the world leaders were around 60 years old, but he was 43.
Yeah, absolutely. That's a great observation. Avery?
What I saw was actually in the top left, Churchill is kind of an outlier because it's not really with Biden and it's not really with Trump or Reagan or any of the others. It's kind of out on the edge by itself.
Yeah, absolutely. He was an early oldster, but he is included. Churchill, Thatcher, Merkel, and Trudeau are included because they are not American, and they are in countries that are have been existing the entire time and are still in existence. One interesting thing that happened in the 80s, 90s, and aughts is countries were declaring independence, and some of them they would declare independence and elect a leader, and that person would be a younger person, somebody representing the new age for that country. And the USSR broke up into different countries around Europe, and each of those countries had a leader who they would have wanted to be someone new, not somebody who had, grown up in the old regime. So there are a lot of drivers. So you can see in 1990, there are some very short arrows, but they're very, very low, lower even than Kennedy. But that didn't start happening until the 90s. So absolutely, leaders are passing through the line of best fit. That's true. That means they started very young and then crossed the line. So the length of your line is how long you were in office. One other thing that I noticed for American leaders is red US presidents tend to be on the older side, and blue US presidents tend to be on the younger side. And that has been consistent over time, except for Truman. So
And by blue and red, you're referring to a Democrat versus Republican?
I am,
Okay.
but I didn't want to go there.
I didn't know. I was just questioning. I just wanted to, it was something I noticed, and I was like, oh, interesting.
Yeah, that happens to be the case. And so it's interesting to understand, like I have mentioned that knowing where you are in a distribution and the difference between where you are and the average of the distribution is really, really important. But if you separate the blue from the red, you can see the red ones are consistently above the line. That's not variable. And the blue ones are consistently below the line. That is also not variable. But when you look at American presidents together, that's where the variability comes from. So like I said, you can create more variability or reduce the variability depending on your assumptions and how you ask the questions. Okay, so this is one of my favorite plots, is our penultimate plot. Let's see if there's somebody who hasn't made a comment yet. Amaryllis?
Huh? Hi.
Was there something about this plot where did your group get to this plot in your conversation?
Yeah, we did actually. We were talking about how this was one of the more like easier ones to read, like for us, because like most of them were kind of jumbled or like kind of hard to read for us. And so like we thought like this was more easier to read because it kind of displays it like how like it's displayed on like the news.
Oh, okay.
Like it looks like the news, and some people watch the news, so that way it's easier,
Well, so this figure is about variability in hurricane forecasting. And we looked in some of our examples, we looked about variability with predicting rainfall, for example. Where is the variability? What are the sources of variability in this graphic?
I would think so. Like, what was variability again?
Variability is the difference between an individual observation and the average. So if the average is the line going through the red dots, then the variability is sort of what's outside that line.
Okay, so then I feel like the variability would be like more like on the top area. So it's like different organizations making their forecast, so like up there, because the line's not really going through it, and it's kind of like over there.
That's true. And if you look at the image, you can see that where it says different organizations are making their forecasts. Those are little dotted lines. The black line is the line the storm actually took. And the variance between, you can see down here in the Gulf of Mexico, one model said they took all the same data, but they did different things with it. And they said, I think this red dot is going to spin out into the Gulf. And another model said, I think this is going to spin off into the Bahamas. But this is where it went. So these are extremes in their predictions. The predictions were based on the exact same data, but their models clearly do different things with the data. other sources of variability are reflected in the red. The red says, here's a model that had, you know, some non-zero chance of happening. It could have gone from here out to here. But this guy also said it was going to go to, you know, North Dakota or whatever state that is, Georgia, or whatever it is. That's unlikely. So the red shows what's sort of likely. White is very likely, and red and black is what actually happened. So there's a lot of sources of variability here, including, if you remember from the rainfall prediction, here's where the storm is right now. Tomorrow or 3 hours, you've seen these plots yourselves. Tomorrow, it could be anywhere in this circle. And then the next day, it could be anywhere in this circle. It's unlikely, less likely to be in the red, and very unlikely to be outside of the red. So there's variability at every data point, and you can see variability in the modeled tracks. Now, again, the math always does the exact same thing. It's which math do you deploy and with what data that drives the differences between these results. Alicia.
Yeah, I just kind of noticed that they all start at the same place and then they diverge more and more as they get away from that point.
That's right. What do you think could cause a modeler to say, oh, you know what, I think it's going to go to the north. I think it's going to go to the south.
Maybe like other weather factors. I don't know.
Yeah, it could be wind. It could be, there could be a mountain in the way. But the thing is that this guy says the mountain is going to make it go to Georgia. And this guy says the mountain is going to make it go to Mexico. So the mountain's there, or the topography of Florida, which is, there's no mountains there. Space Mountain at Disney World is going to make it spin off to Georgia or spin off to Mexico. So this is one of the most interesting things about statistics. These are all statistical and probabilistic models of what will happen when this event, which is happening right now, starts to change over time. It's subject to wind, it's subject to temperature, it's subject to topography. There's a lot of different things. And when you go to school and become a meteorologist, you learn about how all of those things work together. But all those factors will come together in a statistical model that works because there's math, but the way it works depends on what you assume and the roles that you assume those things are going to play. And Camilla notes that they could have observed similar hurricanes. Absolutely. The time of year, the day of the week, the other temperatures will say, oh, that happened last month or last year or 20 years ago. We had these exact same features and it went to Georgia instead of going up the Florida coast. So we think that's what's going to happen. So each of the models differs depending on how you interpret the variables that you have and you put them into your model, but the math is exactly the same. Okay, anybody else have anything to say about how awesome hurricane modeling is? Okay, this is our last graphic. I put a very helpful arrow here for math and statistics. But what did people notice about how, thank you, Jada. What is the, oh yeah, red is the danger zone for sure, but what did people notice about the projected career earnings?
I think Amin and Avery.
Oh, okay.
Amin, if you would like to share.
Okay, thank you. I think like the ones at the bottom are like leaning toward like their earnings are increasing. So like the median is around like that blue, like the dark blue, and like near the bottom, like the earnings are increasing. Like the one that's the most is chemical engineering, and then at the top, like education and social work, humanities, philosophy. Those are like the median is good, but like they're like leaning towards like the less average. That makes sense.
Now this is lifetime career earnings, so over the entire career. What this graph was created to point out was this isn't people who major in education or people who major in social work. You could major in chemical engineering and go into education, or you could major in education, but you're not going to be able to go into chemical engineering if you do that. But if you majored in education, you could take a job in any of these fields. And what they wanted to do in this study was talk about the difference between what you major in and what you do for a living. But I'm sorry, Annika, who else did you identify? I'm looking through the names and I don't see anybody's hands up.
Oh, it says to the left of my screen. Avery, if you want to speak up.
What I noticed is none of
There they are.
no bar goes before the 1.5 million mark. They're all over 1.5 million.
Okay. Yeah, that's so if a person you start your career at age 22 or whatever, and you end your career at retirement and you made only $1 million, that would be really rare, really rare. Probably just as rare as somebody who makes, $20 million, no matter what their major was. Alicia?
Yeah, I just wanted to say that I noticed that the careers that tend to make more in their lifetime are STEM careers.
Shocker. That's true. And math and statistics is down near the bottom in a good way. Autumn?
I have a question.
Okay.
What does the I don't get the percentile.
Okay. Yeah, so these are distributions of values. Each bar is a distribution, and the median is the value below which 50% of all the observations fall. So $2 million is about where the median total career earnings for an education worker would earn over their entire career. That means that 50% of the observations that they had were below 2 million and 50% were above. In the chemical engineering example, 50% of the observations of chemical engineering lifetime salaries, 50% were below $4 million and 50% were above $4 million. Now that doesn't tell you, if you were a chemical engineer and you made $1 million or $2 million over your entire career, it's not impossible. It's just really rare. That would be an outlier value. That's if your career was in chemical engineering. But if you went to college and majored in chemical engineering and went into social work, a lifetime earning of $1.5 million would be in the 25th percentile. 25% of all people in education over their entire careers might be expected to earn $1.5 million. 75% might be expected to earn more than that. 10% would be expected to earn more than $3.5 million because the 90th percentile is at the top. And Yusha noticed that chemical engineering also has the highest minimum compared to the rest, which is one of the items I noticed, is that the lowest, this is the 10th percentile. So 10% of people who work in chemical engineering can expect to make less than $2.5 million over their career, only 10%. That means 90% can expect to make more than that. But 2.5% is the median for criminal justice expected career earnings. So 50% of people who work in criminal justice can expect to make $3.5 million or $2.5 million over their entire career, and 50% can expect to earn more than that. Another thing that I noticed when I looked at this graph is the difference between the 25th percentile and the 75th percentile, sometimes called the interquartile range. But this is the middle 50% of the observation set. This is the middle 50% of the observations is quite tight for education. 25% will make less than 1.75 million and 25% will make more than 2.75 million. But when you look at chemical engineering, the range is more than just $1 million. The 25% of chemical engineers will expect to make less than 3.25 million. But here, the 75th percentile is more than, it's like $2 million more. So the range is much bigger for chemical engineering careers than it is for education. So it's not just the minimum or the spread of the distribution, but also the distance between the 25th percentile and the 75th percentile. So yes, you're right. STEM careers are super high in terms of potential earnings. But I do want to point out that there is the top 10% and the bottom 10% that are not even shown. They didn't even tell you, like, the top 10% of people in chemical engineering make over $6 million. It could be $400 million. It could be anything. We don't know. And similarly for education, the top 10% could make $5 million. We don't know because it's not on this graph. You can't even extrapolate. Okay, so I just wanted to summarize that variability really in practical terms means opportunity. The field of statistics, yeah, neurology would definitely be considered a STEM career, and neuroscience would definitely be considered a STEM career. Let me just answer, this is Amen's question, would neurology be considered a STEM career? When I was in college, I was pre-med and I was going to apply to medical schools, and I was taking a neuroanatomy class, as you do when you're going to go to medical school. I wanted to be a neuropathologist. So I was taking this neuroanatomy lab. We had, our own brains for the semester, and we carved them up and did all kinds of fun things with brains. And I went to meet my advisor one day and I said, I want to go to medical school. Will you write me a letter? And he said, oh, it would be so terrible if you went to medical school, because you will spend 4 years in medical school, then 4 years as a neurology resident, then 4 years as a pathology resident, and then you will get your hands on your next brain. Do you want to wait 12 years before you can start doing brain research? Or do you want to go to graduate school, put your hand in a bucket, and pull out your next brain the next semester? So I said, okay, I would rather do that. I'm going to go to graduate school. He talked me into it in probably 4 minutes flat. So neuro law would be considered applied STEM, because law is technically not a STEM field, but neuroscience is a STEM field. So STEM, I want to point out that STEM is a gateway. Just like variability is an opportunity, it creates opportunity and it represents opportunity. STEM really creates opportunities for you. And as young women and females, you have an advantage over males because you have strong, or the tendency towards strong, verbal abilities. Your ability to communicate is what would differentiate you from another STEM applicant for a law program or a neurology program. So Ayesha says, what are thoughts on actuarial mathematics? Is it worth it? It depends. I think any program that you choose is just the program that you're in. That doesn't mean that's what you're going to be when you grow up. So my first PhD is in psychology, and I do not do cognitive science for a living. I'm a statistician. I use cognitive science to be a steward of science and to teach other people how to teach science better. I absolutely use cognitive science because that's what I did my degree in. But I do not do cognitive science for a living now, even though that's what I got my PhD in. Amen, did you have a question? Yeah.
What's the difference between neuroscience and neurology? Because all I know is that neurology is more of it sides more with medicine, and neuroscience is like more with the actual science.
Right. Neuroscience is any scientific endeavor involving brains of animals, brains of aplasia with the nervous system of a snail, a sea snail, or a human brain or sheep's brain, which is what we did in my neuroanatomy class. Neurology specifically deals with medical complications that happen in your brain. So if you have nerve damage, if you have ALS, if you have MS, if you have Alzheimer's disease, those are all neurological diseases. So if you want to be a neurologist or pathologist, you have to go to medical school first and get your regular MD. So that's 4 years. Then you choose a residency to specialize or get specialty training in whatever it is that you want to do. If you want to do a neurology residency, at the end of that would be 4 to 8 years for neurology. Then you would have to do something called board certification. Board certification in the United States is a national assessment that says Amen is hereby qualified to practice medicine, specifically in neurology. But Rochelle did not pass her boards, so she can be a regular medical doctor, but she cannot practice neurology because she did not pass her boards. So I can't say I'm a neurologist, even though I know a lot about brains. I can't say I'm a neurologist. But if you study in a doctoral program, you would be unable to practice clinical medicine. I know a lot about medicine because a lot of the research that I do is medical. It's for medical applications. So I have to understand risk factors and treatment options. So I know how to read papers that are published for other clinicians. It would be illegal for me to prescribe medicine or recommend any kind of course of action. So the differences between medical training, medical qualification and certification, medical practice, and neuroscience can be very, very different. But with neuroscience, you can pick up any kind of brain. Brains work the way they work. But what you would learn is sort of the different parts, how connectivity happens, what happens if you recover from an injury, how nerves can be damaged, or what kind of nervous conduction you would have. I mean, there's a lot of different things that go on in your brain. How does reading happen in the brain? That was what my PhD was about. What does reading look like in a brain when reading is happening? What's your brain doing? So I don't know if that answered your question, Amin, but Autumn had a question about debating pathology. Yeah, medical school is very challenging. It's not challenging because it's hard, because you guys are all brainiacs. That's not what makes medical school hard. What makes it hard is that every person who graduates from a medical school has to be trained to the same standard. So they tend to tell you all the same thing and ask you to do the same thing so that you're all the same. Everyone who has an MD is the same as everyone else who has an MD. And to my personal opinion, it tends to blunt the spectacular differences, especially for smart women and men, mostly women. It tends to make you more similar. And I don't think that's a great thing. And when I work with students who are brilliant and women, I want them to go into research because it's a creative field. They don't encourage you to be the same. They encourage you to think differently. You have to think of something no one's thought of before. Whereas in medicine, thinking of something that no one's ever thought of before is going to make you diagnose, Ebola, which is super rare, in someone who has, chipped their fingernail polish. That when you are being creative as a clinician, it can be very difficult. But in science, it's needed that you are creative. So I always try to encourage people to think through their choices of going to medical school versus graduate school. However, if you go to medical school, you will have a guaranteed job. You can work anywhere. You can go to Médecins Sans Frontières and work in different areas of the world and help have promote justice and equality of healthcare and deal with global epidemics and do all kinds of things that I personally cannot do. I wish I could, but I can't. So having a medical degree is super valuable. Having a scientific degree can be really hard, but at least you're intellectually challenged and free. It's a choice between intellectual creativity and job security, because there's not a lot of job security in academia and academic science. But you can go into industry and then it's all bets are off and you make a giant pile of money. Avery, you absolutely can leave. Thank you very much. So I want to stop here and tell you that I appreciate your time and your attention. I want you to recognize, embrace, and understand how and when you differ from what's expected. That's the whole point of this whole talk, was to recognize diversity and variability and embrace it. Outliers represent variability and the potential for change. That's the only way change can happen for yourself. When you recognize where you are and where you want to be, that's the only way that you can change purposefully for yourself. But you can also be a change agent when you recognize what's expected and average and what else is possible. That's really important. And I want to encourage you to think about this quote from Gandhi. You may have seen "be the change you want to see in the world" as a quote that is attributed to Gandhi. But in fact, what he said was, if we could change ourselves, the tendency in the world would also change. As a man changes his own nature, so does the attitude of the world change towards him. We need not wait to see what others do. We can be change agents, is what Gandhi was saying. And I want to encourage you to do that and to challenge expectations for yourselves and for women. Okay, so now leave if you need to. We're done. I told you what I wanted to tell you. And if you have other questions, I'm going to stop sharing and then we can chat about what you want to be when you grow up.
Thank you. This is such a great way to like end Gem Hunt the week. I think it's really great to like sort of, establish these life lessons. I think it's definitely,
Well, thank you. And thank you for inviting me.
Yeah, of course. I guess if anyone else has questions, they can ask.
Yes, please do.
Thank you for the lesson. I'm gonna head out. Bye. Have a good day.
All right, you too.
Well, I think it's been a great week, and I certainly appreciated the talk today. And even in my, older years, I try to be the change too. So I encourage everyone to, be the change and look on beyond what you think you can even do and reach for the stars.
Expected. Absolutely. Amen, did you have a closing thought?
Yeah, well, you said in the beginning of the presentation that you're like, when I mentioned that I wanted to be a neurologist, you said you were gonna like connect.
Oh yeah.
Some people.
Yeah, absolutely. So I work in a department of neurology and I am not a clinician. So you don't have to go to medical school for that to happen. But if you do want to go to medical school, you want to find someone who is a clinician, a neurologist preferably, and see about, especially if you're not in high school yet, you want to look at medical school admissions and see what they need to make sure that you chart a path from where you are to where you want to be. If you have the opportunity to take a neuroanatomy lab or other, I'm going to say hands-on. I'm not really sure what that's going to look like in a COVID world, but learning about how brains work, you can look at imaging studies because imaging studies show you what's in the brain. If it's a PET study, it shows uptake of glucose, so that's what's active in the brain. fMRI is functional magnetic resonance, so that also shows what kind of activity is going on in the brain. There's a lot of different things that you can do to orient yourself to brains. And as you learn about these imaging and assessment methods, you can then, decide, well, I want to use fMRI for research or whatever. And Autumn says you should take anatomy and physiology when you get to high school. If you can, 100%, you absolutely should. You should also take calculus, physics, and chemistry because those are definitely going to be on the entrance exam. Ayesha, did you have a question?
This doesn't have anything to do with STEM, but with Georgetown, because you mentioned that you work there.
Say it again.
It's sort of with Georgetown, not with STEM. So for the summer program, is Georgetown offering any, not just with STEM, it can be with law and politics.
You know what? I have been getting emails. I got 2 emails. Bye, Julie. Thank you. I got 2 emails this year from high school students wanting to work in my lab. I don't have a lab, and to work with me, you have to have a PhD at least in a quantitative field. So I cannot take students in my lab. But I know the guy who he is a neuropathologist, and I think he takes students, not now because of COVID, nobody can come to campus. So they don't know what's going to happen in the fall for people who are around 16 years old, because that's the cutoff for the vaccine. So I can't really speak to what's going to happen for the next year or so, but I would look around for people who have a web presence. So this guy, his name is Brent Harris, Harris. He is a neuropathologist, and he may have space in his lab where not in college yet students can go. There are at least 2 neuroscientists at Georgetown who do take high school students into their labs in the summer. I can't remember who they are right now, but I know I've heard of them. And then there's a guy called John. His last name is Van Meter, Vanmeter, and he runs the imaging research group for the Georgetown University Medical Center. But there's also Howard University, which is right up the street. There's American. There are a lot of universities around, Johns Hopkins, that have, and University of Maryland, that may have people doing the kind of research that you're interested in, and they may have opportunities for, before you get into college, to come and spend some kind of a rotation or do some sort of a thing in their labs. That I do not do that, and I can't think of anybody who does, but I mean, off the top of my head, but I know that if you look for them, this is what you're looking for, is somebody who's doing the kind of research that you're interested in. So neuroscience or neurology, neurosurgery, neuropathology, whatever, and email them your resume, tell them you're interested in a summer opportunity to work in their lab and learn more about what they do. But read about what they do, because I get probably 5 emails a week, and most of them are random. They'll say, I've done research in cancer. I really want to work with you. Well, I don't work in cancer. I don't know why you want to work with me. So do some homework before you email them, but definitely contact them, make contact. So I connected a young junior in high school, I think he is, with a colleague of mine in the biostatistics department who he might end up working with. But that's because he told me what he wanted, what he was interested in. If you just send a random blast of, here's my resume, do you have a spot? The likelihood is low that you will.
Thank you.
Any other questions? Oh, thanks, Aisha.
All right, I think with that, we will wrap it up. Does that sound good, Anika?
Yeah.
All right. Well, Dr. Tractenberg, I can't thank you enough for your time and your ability to work with the students is fantastic. So I hope you got as much out of it as I know they did. So you want to wrap up your 5-day event here, Anika, so go for it.
Well, I think this is it. We'll send a post-event email, right? So everyone will get like the survey and everything, right?
I want to encourage everyone to fill out the survey. It's super, super important, just as important as it is for you to recognize where you are and where you want to be, so that you can make a plan for yourself to get better. Whenever anyone asks you for input, you can do whatever you can to help them get better. Specifically, if only Dr. Tractenberg had stopped talking 20 minutes early, this would have been so much better. If with that kind of input, that I can get better, this program can get better. So if you have specific feedback, I want to encourage you, whenever you have feedback, you should give it. It's always helpful.
Yeah, thank you. That basically summarizes it. And we'll send it in a post event email, so you should get that really soon. Yeah.
Okay. Yeah, we just need to finalize it and then we can email it out. And there are prizes. There'll be raffles for prizes. So there's all more encouragement to take the survey.
Okay, I think that's it now.
Thank
That's a
you.
wrap.
Bye.
Bye, y'all.
You have a great
Bye.
Thank
Bye.
you.
Thank you so
Bye.
much.
All right.